right, guys, here it is. Bayes' theorem. That's Thomas Bayes right there. That fabulous picture of him. He lived in I think 1701 to 1762, something like that. Back when it was in the 1700s. That little experiment we did with the beanbags, that is the very thing that he did. And I got the idea to do that from a number file video. You guys ever watch number file? Yeah. To be honest, I'm not 100% sure it was a number file video, but it was some of the same people. It was Hannah Fry and Matt Parker in the video. Hannah Fry, she's the redheaded girl that you've probably seen a lot of number file videos. And then Matt Parker, he's the guy that does the stand-up comedy math videos. He has like stand-up comedy about spreadsheets. It's actually very hilarious.
The lanky guy or the curly hair guy?
Neither.
I don't know.
Matt, if you're listening, you may be lanky or curly-headed. I don't know which one that is. Not that he's ever going to see my videos. Anyway, they did the experiment. They actually did the experiment, the exact same one that Thomas Bayes did. And so the idea, again, as we talked about, is to update your understanding or your belief in something, right? We all have a belief in different things, right? And that belief changes over the years, right? Maybe your belief in what is the best diet for you has changed over the years, right? I grew up, my mom is from the South. I grew up eating, biscuits and gravy and fried food, and I just thought that's the way people ate. I believed that was the right kind of food to eat. Now, 2 decades later and diabetes later, my belief in that diet has changed, right? So now I've experimented with diet like the keto, and this is not a diet course, guys, but it fits into this Bayesian idea. I've experimented with different types of ways of eating to control diabetes, and I've had a lot of success with the keto diet, right? So hashtag keto for life. What'd you guys talk about in class today? Like serial killers and diets. It's all Bayes related. Anyway, but I've updated my belief in the value of that kind of diet for me. It's been very effective for me. And so my belief has been updated, but it comes with things that can be plugged into Bayes' formula, right? It's hard to say that, Bayes' formula, right? But it comes from getting more data. The whole idea is the more data you have, the more accurate you can be in your belief. You'll never be 100% though, using Bayes statistics anyway. There are some things that you can be 100% sure on, right? When you have all the proof and the evidence. But using Bayesian logic and Bayesian formula and statistics, whatever you want to call it, you can't be 100% sure. But this helps you hone in on it and get closer and closer to 100%. And as with the beanbag experiment, and if you're watching this video and have no idea what we're talking about, look in the video description below. There'll be a link to that beanbag experiment. But with that beanbag experiment, if there were an infinite number of beanbag tosses, eventually you could get almost 100% certain where that other beanbag was, right? All right, so let's dive into this. Enough preface here. We're going to do a brief review of conditional probability from the last couple lectures, right? We're going to see how Bayes' formula is derived from the conditional probability formula. We're going to try to understand the formula. Then we're going to apply it. We're going to look at a probability tree, practice, and then we'll talk about Bayesian thinking a little bit more, which is the stuff we've just been talking about, right? So I want to ask you this question first, and I'm not going to give you the answer right now, but I want to just sort of take what's the word, an informal poll, right? If you take a cancer screening test, and specifically the cancer test we're looking at is breast cancer for women between the ages of 40 and 50. That's the specific one we're talking about. If you take a cancer screening test and the results come back positive, what is the probability or what are the odds that you actually have cancer? Okay? Now, I don't expect you to know that. Some of you may be familiar with this idea, but I'm going to write on the whiteboard here, and maybe I'll do an overlay on the computer here to show the numbers we came up with. So after pulling the class, we've got a few numbers here that you should be seeing on your screen right now. You'll see there's a wide variety of them there. We will answer the question at the end of the lecture. So stand by and stay awake. Answer, just told you, end of the lecture. All right, so here we go. Review of conditional probability. We're going to do this very quickly. You guys should know these. Let the following be events when rolling a standard 6-sided die. A is you're rolling an odd number. B, you're rolling an even number. C, you're rolling a number greater than 4. And then D, you're rolling a 5, all right? without even having to use the formula, we can answer these questions pretty easily because the sample sizes are very small. What is the probability of C? Right, you're correct, it is 1/3. Let's speak in terms of the actual size of the sample set though. So what would that be? 2 out of 6, right? And yeah, of course you would want to reduce that down. But I just want to make sure that we're all on the same page, so it's 2 out of 6 is your probability. All right, probability of C given A. So what the question is saying, what's the probability that you're going to roll something bigger than a 4, given that you did roll an odd number? 1/6. No, 1/3, sorry, you're right, it is 1/3. Yeah, don't listen to anything I say, I don't know what I'm talking about. 1/3 is correct. Why? Because our sample set is now 1, 3, 5. Only one of those is greater than 4, right? Good? Okay. Probability of D given A. Probability that I rolled a 5, given that I rolled an odd number. Yeah, that's the exact same question as the one right before it. Probability of C given A, I'm essentially saying, what's the probability of me rolling a 5? That's the only odd number greater than 4, right? So those are the same. Probability of D given C. So probability of rolling a 5, given that I rolled greater than 4, yeah, sorry. 1/2, right? Probability of rolling a 5, given that the number is greater than 4. Well, if the number is greater than 4, that's the given. What's our sample set? It's just 2 things, right? 5 and 6. One of those is the 5, so it's 1 out of 2 shots, right? And I'm going to put the numbers on the screen in a moment. And then the last one, probability of B given A. 0, right? The probability of me rolling an even number, given that I rolled an odd number, obviously that's 0, okay? And these are the answers here. We probably should have been playing them as we went along, okay? Look at those, make sure you understand why those are all true. We understand them? Okay, this is the review part. We should be familiar with this, but if we're unclear, I want to make sure. We good? Okay, let's take a look at a couple more here. Let these be the events when drawing a card from a deck of cards. You picked a spade, or you picked a black card, you picked a court card, you picked an even card, you picked a queen. So what is the probability of each of these events? Probability of A given B. So probability of it being a spade, given that you picked a black card. Now, you have to be familiar with the deck of cards to answer these. I'm assuming most of us are. But just in case, right, there are 26 reds, 26 blacks. The black cards are 13 clubs, 13 spades. Red cards, 13 diamonds, 13 hearts, right? So what is probability of A given B? 1/2. And what's the original numbers we would have there? 13 over 26, right? Which is 1/2. Very good. Okay. Right, so 13 of those spades, you have 13 spades to choose from, and we know we picked a black card, which means our sample set is 26. All right. Probability of E given C. Picking a queen given that we picked a court card. Courts are jack, queens, and kings. 4/12, yeah, very good. Or 1/3, exactly what you just said. You looked at my slide in ahead of time. Good. All right. What is the probability of not picking a queen, given that I picked a court card? 8 out of 12, right? Which is 2/3. Make sense? If any of these numbers are unclear, stop me and we'll make sure we understand, okay? Next one, probability of picking a court card given that I picked a queen. 100%, right? Because I know it's a queen. What's the probability that a queen is a court card? It is always a court card, right? Very good. 100%. 4 out of 4, right? And let's make sure we understand that 4 out of 4. Probability of it being a court card given that it's a queen. Well, if it's given that it's a queen, assuming this is a normal deck, there's 4, that's your sample set. And what's the probability of me picking a queen when I've only got 4? 4 out of, there's 4 chances I can pick a queen, so it's 100%. All right, last one, probability of picking a court card given that it is not a queen. Very good, 8 out of 48. You see why? Right? It's not a queen, so that eliminates 4 cards from the deck. The deck's 52, right? You minus out the 4 queens, you got 48. That's your new sample set. Given that it's not a a queen here, right? So this was the given. It's not a queen. Given that sample set of 48, what's the probability that I'll pick a court card? Well, there's only 8 cards left in that deck of 48 that are not queens, right? Or that are court cards, I should say. Which does give us 8 out of 48, which is 1/6, all right? That's the review portion. We feel okay about that? Let's remind ourselves how the equation works. This is the probability equation, right? And we're gonna look at 2 Venn diagrams here to help. Again, this is all memory triggering, hopefully, to remind us of what we talked about last week. We had this exact slide last time, right? So just briefly, let's look at this. The universe is the whole lavender box, and it's all possible flips of a set of 3 flips, right? I flipped the coin 3 times. There's only 1, 2, 3, 4, 5, 6, 7, 8 ways that can pan out, right? You can see all 8 ways that I can get 3 flips right there. Assuming it's there's only a head and tails, there's not going to land on its edge, right? Okay, then you see that E is a number of the number of flips that have an odd number of tails, right? The E in the Venn diagram, and then F is where the first flip was a T. If you remember, the question was, what's the probability of us having an odd number of tails given that the first flip was a tail? Well, where is that on the Venn diagram? That's the intersection right there, right? Okay? That's where we get this formula. It's this divided by this, right? Because the F is this stuff right here, that the first flip is a T, a tail. And I'm asking, what is the probability of this, of E happening, and what is E? It's an odd number of tails, given that F did happen, right? Given that F happened, that's what that piece means. Well, it's the probability of that intersection, which is right. What's the probability of this happening? Given that that happened, the answer is this divided by this. That make sense? Okay, let's look at it with the playing cards, because that's an example we just saw a second ago. All right, this is an entire deck of cards right here. I didn't want to make a single ace and 2 and 3, so I just did ace through king, right? But this is the entire deck of cards. Now, the universe is all 52 cards. We're leaving out the jokers. A is that it's a spade. B is that it is black. The red ones are neither of those things, right? So our question a minute ago was, what's the probability that it would be a spade given that it's black, right? So what is the probability that it will be in this circle, A, given that we know 100% sure that it is in B, right? Notice when I draw my little blue lines, I end up with that intersection again. Those blue lines are making their own Venn diagram, just squares instead of circles. So in other words, it's this number divided by that number. Well, this number is the intersection of A and B, and this number is B, or the probability of that intersection divided by the probability of that intersection, of that set. Make sense? That's the formula. That's what we talked about last week. Hopefully that's pretty clear. That's a review, but this is the foundation of Bayes' theorem, okay? So here's that formula one last time here. Now, would you agree that that is the same thing, just algebraically, right? Would you agree that that's also the same thing? Now take a minute and look at this one, okay? The part that throws people off here sometimes is this. I'm saying the probability of A given B times the probability of B is the probability of the intersection. Remember that the probability of the intersection of A and B is the same thing as the probability of the intersection of B and A, right? The order of the A and the B when you're dealing with intersection is irrelevant. So I'm keeping it in the same order there, right? I could have, if I wanted to make it seem a little more clear, reverse the A and the B there, but it mathematically doesn't matter. Dig it? So this formula, we agree that both of these formulas are correct and accurate, all right? Because I'm going to erase the top one in a minute. I want to make sure we buy into this. Okay, good. All right, so with everything on the screen here, now look at that third one. Would you agree with that statement? All we did here is replace this. So here we started with this formula here. We still kept this piece of it right here, then we would just replace this with this value, which came from this formula. Agreed? All right. So here's that formula again. We're just going to keep that front and center for a moment. And we're going to change the color to make it fancy. Okay. Would you also agree that that's true? Just algebraically rearranging stuff here. That's all I'm doing. A little bit of substitution and some algebraic rearrangement. The probability of B given A is equal to the probability of A given B times the probability of B divided by the probability of A. That's Bayes' formula right there. Okay? We're going to see how it applies, but there's one extra piece we need to account for. Okay? But that is the theorem, right there. The last thing we need to take a look at here is this right here. Getting the probability of A given B and the probability of B, usually those are easy things. They'll just be known facts or whatever. But what is the probability of A in whatever question we're trying to answer? That gets a little tricky. We have to deal with total probability, and we're going to look at some probability trees and some ways to figure that stuff out as we move along. But normally, the top part of the equation, the numerator, is pretty much stuff that will be given, or with the data we have, it's easy to figure out. Calculating the denominator gets a little trickier, all right? And if you remember, when I first introduced you to probability, what did I say? It's just favorable outcomes over possible outcomes, right? Or we use the more formal terminology, which is events over sample space, right? Well, and I also said that that's easy, right? It's something divided by something. That's an easy thing to calculate. What's hard is figuring out what is the E, what is the S. And now I've made it even harder, right? Because we're expanding this, okay? But it's still the same thing. It's something divided by something. That's what probability is. So let's sort of generalize this just a little bit here, all right? We've got these two, they're the same equation here. We just rearranged them in one case. But we're going to do a little bit of playing around here, okay? So let's take a look at a Venn diagram first. This is just some universe of some events, right? I don't know what the events are. It doesn't really matter. We're just going to be general here. And our Venn diagram shows event A1, event A2, A3, and A4. Notice here that all four of those events, if you add them all up, you get the entire universe based on this Venn diagram, right? Most of our Venn diagrams, we got the two circles in the middle, and there's still a whole universe where there's stuff that isn't necessarily in our events. But here I'm saying that event 1, 2, 3, and 4, if you add them all up, it is the entire universe. Agreed? Okay. Now we have another event called B. Okay? This event occurred. This event is not the entire universe. Agreed? I want some nods on this stuff to make sure we're good on this, because it's going to get a little more tricky as we move along. That yellow section right there, how could we describe that in terms of set notation? What is that? The intersection of B and A1. Very good, right? Everybody see that? The intersection of A and B1. Okay, now you know that. I think the next one should be pretty easy. How about that dark blue? What is that? Yep, A2 and B, right? Okay, and then obviously the next ones, though each of those sections. Do you agree with those pictures? I tried to color code them, and this thing's going to get pretty colorful and get a little messy, but do we agree with everything on the screen? Do we understand it? Okay? And I apologize for asking that question 1,000 times, but I want to make sure that as we move along and we get to the final Bayes formula, that you just believe in it, right? I'm trying to update your belief in Bayes' theorem, okay? All right, there's a little self-referential humor in there. Yeah?
So the entire universe in this case is A1, A2, A3, and A4.
Added together, yeah, yep, exactly right. Now, we could, if we had an expanded universe that was bigger than that purple lavender thing, then maybe we might see that A1 box finally closes in and there's some stuff outside of the A1 box. But this particular thing, so take, for example, the idea of a universe of flipping a coin, heads and tails. I could split that Venn diagram right down the middle, and one side's heads, one side's tails, and that is the entire universe, right? Mm-hmm. That term for this is, and I think it comes up on a slide in a minute, is mutually exclusive and collectively exhaustive. That word collectively slipped my mind. Mutually exclusive, collectively exhaustive. So what I mean by that, think about again the heads and tails. If you get a head, you didn't get a tail, right? They're mutually exclusive events. You can't get both, right? I cannot get A1 and A2, right? They're mutually exclusive. They're collectively exhaustive because if I get a head or a tail, that's the entire universe. There's no other part of the universe. So whatever A1 is, again, I'm trying to generalize here, so A1, who knows what that is, right? But it's A1 and A2 and A3 and A4 is the whole universe, okay? Good? Good question. So now we got B, and we can define B as the intersection of itself and these other pieces of the universe. Agreed? And those four little things on the right there. Would you agree that B is equal to the intersection of 1 and B, the intersection of 2 and B, right? Would you agree with that formula on the screen? Makes perfect sense, right? All right, if that's the case, then, and there's, I told you those terms are going to come up. We understand those two terms there? Don't need to explain those again. Yeah?
Is there a universe subscript, so you did A subscript U? Is that how you define the whole universe? Like, how do they do that mathematically, or is that just...
A universe, well, so you're asking how they define a universe? Well, yeah, if you're talking about a whole universe, you can use whatever variable you want, but typically they will use a U.
Okay.
Yeah, so the universe in this case, U is equal to A1 plus A2 plus A3 plus A4, correct, yeah. Yep. All right, other questions about this picture here? We're gonna add a piece to it, so I wanna make sure we're good. If that stuff in black there is true, then isn't the stuff in blue there also true? The probability of B happening is whatever the probability of yellow happening, plus the probability of dark blue happening, plus the probability of that green, plus the probability of that light blue happening. Do you agree with that? Yeah? Everybody? Yeah? Okay. Questions about that? All right, now, it's going to get crazier here, okay? I just want to make sure, baby steps along the way. So we're going to take that formula that we all agree with, that Venn diagram helped us derive this using stuff we already know, and remember this formula here, okay? This is our original probability formula. Okay. Probability of B given A times probability of A equals the intersection, which we know this to be true. We looked at it in a previous slide, okay? So we good so far? I just want to remind us of what these formulas are because we're about to do some substitution here. It's going to get a little messy. All right. That term right there, the probability of something intersecting the other thing, or that, or that, or that, would you agree could be written that way? Because what I have here is the probability of A intersect B. Well, I have a bunch of A intersects B. I have the probability of that one, and this one, and so on. Well, I could substitute this for this. It's the same thing. Agreed? Why, Jeff? Why are we doing this? I promise, we have purpose. So now I've rewritten that stuff in blue above to that new equation that's kind of smaller there. Assuming I didn't make any typos, and using this as our starting point, knowing that for all the intersection probabilities, I plugged in this. Do you agree with this formula here? Take a moment to look at it. So that being said, we've now used our famous sigma notation here, and looking here, what I've done is I've changed this to go from 1 to 2 to 3 to 4 to 1 to 2 all the way up to subscript n. In other words, the probability of B occurring is that. Do you agree with that? Obviously, I could also do the same thing with the probability of A, right? Agreed? So if we were looking at events where I want to know the probability of A, then of course, this would be an A, this would be an A, this would be BI, and this would be BI, right? So you understand that that's the same idea? We feel okay about that sum formula there. Okay? That is total probability of B. That's what that concept is total, is called total probability. So let's look at what's, I'm going to surprise myself. I don't remember what the next slide is, but it's going to be fun, I promise. All right, that's just me moving stuff out of the way, okay. All right, so this is the total probability. Well, what we're going to see in a minute, when we look at the probability where, with Bayes' formula, where the denominator is the probability of B, we're going to plug that in instead, right? Because remember, probability of B given A is equal to the probability of A given B times probability of B divided by probability of A, right? So we can use this for the denominator. This formula here, again, this is the one I just sort of recited a second ago, and this one. Do you agree that this is the same idea, right? I just rearranged it. So this is a scenario where we're going to use that to plug in right here, okay? So I'm just putting the formula on the left, but it's the same thing. All right, since we all understand this formula, we agree with it, we're going to substitute that, as I mentioned, for the denominator of the original formula there, and now this is the final, complete Bayes theorem with everything generalized. There's one little thing we need to tweak, which is that adding the subscript for the A's there, right? So the probability of A subscript I, given that B did occur, is the probability of B given A subscript I, which is not subscripted, but it should be, and I'm not going to fix it, times the probability of A given, probability of A divided by that whole mess we just walked through. How do we feel about that? That is the final generalized formula. Let's take some applications of it. We have here some statistics that are made up. I made these up. I don't know if they're real or not. Okay, they're based on some reality. But here's what we're looking at. We have criminals that are ranked from low risk of recidivism, right? They're low chance that they're going to go back to prison. There's a medium chance they'll go back to prison, and there's a high chance they're going to go back to prison. Okay, the first row there is the percentage of low-risk criminals. 35% of the criminals are low risk. 55% are medium risk. 10% are high risk. Okay? Then the actual percentage of recidivism rate. The low-risk criminals have a 2% recidivism rate. Okay? So think about that for just a minute, make sure we understand that number. We have 100 criminals. 35 of them are low risk. Of those 35, 2% of them will actually commit crime again. That makes sense because they're low risk, right? Medium risk criminals, of those 55%, 9% of them will commit a crime again. And then of the high risk criminals, which is a very small group, there's only 10% of the criminal population are high risk, but 20% of those 10% will repeat offend. Okay, so we understand the numbers though, and now if I were to ask you something like, what's the probability that any given randomly selected criminal, so the entire criminal population is randomly grab one, and what's the probability, and he has reoffended. So I grab a random criminal who has reoffended, what's the probability that that criminal is low risk? That seems like a hard question to answer, doesn't it? We can answer it now with Bayes' formula. Okay? We can plug this in. So let's look at how this would all apply. So here's our formula again. I just moved it down so we can look at it. Now let's plug in what we know. What's the probability of B given A? And again, that should be subscripted. I'm not going to change it. I'm just going to keep reminding us that it should be a subscript. I must have missed it when I was making that slide. What is the probability of B given A? Well, what is it? What's the probability of A? What is B and what is A in this scenario? So the thing that we know is that they are a reoffender. That's the given, right? So we want to know the probability that they're low risk given that they're reoffender. So A is our low risk, B is their reoffender, right? Does that make sense? So if we just, I think I changed it, yeah, I changed it to look like that, okay? So we're asking, what's the probability that you're low risk given that you are a reoffender? That is equal to the probability of being a reoffender given that you are low risk. times the probability of you being a low risk divided by the probability of you being a reoffender. Now, look at the numerator there. That's pretty easy. I think we can see that those numbers pretty simply. What's the probability of being a reoffender given that you are a low risk? That number is given to us. What is it? 2%, right? The probability of being a reoffender given that you are a low risk is 2%. That is exactly what these numbers mean here. These numbers mean what's the probability of that given whatever one of those you are. That's what those numbers are, right? So that's easy enough. What is the probability that you are a low risk criminal? 35%. So the top is easy, right? It's 2% times 35%, right? That's pretty easy. Okay. Probability of being a repeat offender. That's a little trickier. Well, knowing what we know about the total probability that we've been spending the last few minutes on, and that with our sigma notation over there, how can we answer this?
Wouldn't it be what we did for the numerator, except for the rest of them as well?
Exactly right, yeah. So it's the probability, so we got these two numbers, very good. We got these two numbers here by multiplying these two numbers, right? And do we understand why that is? Because that is the probability of B given A times the probability of A, right? Well, we want to know the sum of all of those. So we want to know the sum of that plus the sum plus that plus that. That will be our denominator. Does that make sense? So we have that for our denominator. Do you agree with that? Do you understand it? Whether you agree with it or not, it is true. So the real question is, do you understand it, right? Yeah. So now let's do a little bit of math here, and let's just kind of shrink this stuff up a little bit. We get those numbers on the bottom. I just did the math for you. If you want to plug them in your calculator and verify them right, you can. And then let's combine them a little bit more, and we get, ultimately, we're going to have this divided by that, 0.007 divided by 0.0765, which ultimately gives us a 9% chance that we are a low-risk criminal if we've reoffended. So when we look at the fact that 35% of the criminals are low risk, but the recidivism rate is low, and so this disproportion here is what makes that number go a lot lower than we might have thought. If we were to do the same thing for a high-risk person, we'd see a lot higher numbers here, but they won't necessarily be what we might have thought. Now, how many of you, and maybe the answer is yes, but that's okay if you did see this. If you didn't see it, it's also okay. But how many of you thought, well, obviously it's going to be around 10%? Or did some of you think it's going to be higher? Or some of you think it's going to be a lot lower? Anybody want to throw that out real quick? Any thoughts on that?
I thought it was gonna be lower.
Lower, okay. Like how low? Like 1% or something like that? Or
More like 5.
like 5? Okay, about half. So yeah. And I don't mean this like negatively, but that's way different than what it actually is, right? It's way off. And so a lot of times our intuitive thinking is off until we actually apply the numbers. And so that's why this formula is so important, is that it helps us see things that are right there that we didn't recognize. And we're going to see that when we get into this other question we asked about earlier. Now, so again, the question was, what's the probability that any given randomly selected criminal who has reoffended is low risk? And it seems like it would be pretty darn low. And 9% is higher than I would have thought too. Okay? Okay, very good.
Bad at taking percentages of percentages in our head.
Yes. I know when I first asked the question, I noticed you just threw out some numbers right off the bat. Where did those come from? I'm curious.
Oh, it was the multiplication of like the 2 over 36, because I knew we had to take the percentages. I just kind of guessed it was somewhere in there.
Oh, what does that all end up being? Is that close?
It was like 2 divided by 36. Let me see if it's 9%.
Where are you getting the 36 from?
Oh, I was just adding up some of the percentages. It wasn't
Oh.
completely, it was just kind of a guess.
Oh, okay.
I was throwing
Well,
out.
I'm curious of what that ends up being.
Let's see. So like 2 divided by. It's like 5%.
5%. See?
5.5%.
Yeah. And then the reason I wanted you to calculate that is because it's just more evidence that oftentimes we look at the facts and our natural brain thinks, oh, yeah, it's about this. And sometimes we're way off. We were off by about half, right? So that's why this formula is so important. Okay, good. I'm glad that we did that little experiment there. Okay. To the whiteboards. Looking around the room, it looks like we all got it correct. Let's just make sure real briefly. This is the question that's being asked here, and it's always good to form the question in terms of variables that make a little bit more sense. So I'm asking, what's the probability that the marble came from bag one, given that it was red? That is the question that's being asked. And if you substitute the words bag one in red throughout the formula, you'll get that little green thing on the bottom there, right? We can plug in the top numbers. That's pretty easy because we know the probability of it being red, which was 2 out of 6, given that it came from bag one, which is 2 out of 6, right? We can see that by looking at the picture. And we know the probability of picking bag one, which is 8 out of 10. That's pretty easy. The bottom one, we have to sum everything up, right? Just like we did before. So I have to multiply whatever the probability is here, which is 2 out of 6, times 8/10, right? Plus 1/3 times 1/10, right? Plus, if I remember right, that's 5 out of 9. There's 5 reds and a total of 9 marbles, times 1/10. So you multiply and add all that together, and that will be your denominator, right? And so I think I just plugged in those numbers for you like that. Does everybody understand that? Hopefully, I think you do because you all got it correct. And I'm just going to walk through the math real quick on the different slides, but the top will evaluate to 16 over 60. The bottom will evaluate to those. We find our common denominator of 180, add it all up, and you end up with that equation on the right. Long story short, when the math is all done, you end up with 75%, which I saw 3/4 all over the boards. You guys got it correct. So we understand that. I think we're good there. Let's look at another way, though, that we can figure out the denominator, right? This is a probability tree. So I moved the bags out of the way, the pictures, and I just put on the right there, the probability of 1 is, for the actual reds is 1/3 of red, 1/3 of red, and 5/9 of red, okay? So we have a starting point, and what a probability tree is a binary decision tree. Sometimes it's trinary, which is kind of going to be right now, right? So what's going to happen here? We've got 3 choices with our starting point, picking a bag, right? So 3 branches. I could pick bag 1, pick bag 2, or pick bag 3. From bag 1, it is binary. It's red or blue. That's it. And by the way, we know that there's an 8/10% chance I'm going to take, or an 8/10 chance I'm going to get 1, and so forth. I just plugged in those numbers in, right? Okay, now once I'm in the bag 1, bag 2, or bag 3, I will make a decision to either pick the red one or the blue one. And I say make a decision, but this is all blind, right? I'm not looking in there. Because if the probability of me getting a red when I'm looking and I can see what ball I'm going to pick, well, it's going to be 100% because I'm going to pick a red one, right? So that's not what we're asking. We're just saying if you're blindfolded and you reached in and just randomly grabbed one, okay? So what's the probability from bag 1 that it's going to be red? We know that number, and it's on the right there, and we'll look at it in just a moment. But as you can see, from bag 2 and bag 3, again, we'll either pick red or we'll pick blue. So this little binary tree, not binary, this decision tree can help us make a decision of what the, what's that? It's a weighted graph, yeah. All right, so now, and it's also a tree, because there's a root and there's no loops, right? And a tree is a graph. Okay, so now we can put those values where they belong, right? 1/3 of the time you'll get a red in bag 1, also in bag 2, and then 5/9 of the time you'll get a red in bag 3. Right, I'm just going to clean that up a little bit there. And then if that's the case, if 1/3 of the time you get red, that means 2/3 of the time you'll get blue, right? We agree with all the numbers on the graph? So you can draw this kind of a picture to help you get the total probability for your denominator when you're doing a Bayes calculation. Now, what we're looking for, again, it's the path to red. We're going to add up all the paths to red. Well, what are the paths to red? Well, there's the first path that goes 8/10 to 1/3, right? Or 2/6, plus the path that goes 1/10 to 1/3, plus the path that goes 1/10 to 5/9. I got those not in the right order there, but you get the idea. Do you see that? To the whiteboards. Looking around the room, I think you guys got everything correct. So here we go. Let's look at the one on the left here. Notice what I did. I substituted out variables that seem to fit a little easier rather than trying to say A equals this and B equals that. I said V for vegetarian, B for broccoli eater, right? So the probability of being a vegetarian, given that you eat broccoli, is the probability of eating broccoli, given that you're vegetarian, times the probability of being a vegetarian, divided by the total probability of being a broccoli eater, right? We all agree with the equation? We can do now some plug and play here and substitute the top two numbers. Those are always easy to get, right? What's the probability of being a broccoli eater given that you're a vegetarian? That's bullet point number 2, right? Probability of being a vegetarian, bullet point number 1. So the givens are there. Now, what's the probability of being a broccoli eater? Well, there's two kinds of broccoli eaters. There's vegetarians and there's non-vegetarians, right? Okay? So how do we figure this out? Well, we're going to use a tree for this. And this is a simple tree. And remember, the trees always, wherever your starting point is, you're going to make whatever possible decisions there are. And then once you arrived at that place, you can make whatever possible decisions are next. So in this case, we started off with this starting point here, and we decided to make the decision being that there are vegetarians, 25%, which I'm not sure how to get around that box there. Sorry about that. And then 75% are not vegetarians, right? You have one or the other. Once you get there, then 80% of these vegetarians here eat broccoli and 20% don't. 40% of the non-vegetarians eat broccoli and 60% don't. That's it. What we're looking for is the total probability of being a broccoli eater, okay? Well, we just look at the paths. There's the blue path right there, right? And then there is the green path. We add those two paths together. First, we multiply the numbers along the way, so 0.25 times 0.8 plus 0.75 times 0.4, right? We get this formula right here. That's our total probability, okay? Which is 0.5. We can do all the math. Do the math completely, and you get probability of being a vegetarian, given that you eat broccoli, is 40%. Questions about that? Pretty straightforward, I think. It's mostly plug and play. It's just about recognizing what data do I actually know, and what can I figure out. Because I can figure out what the total probability of whatever my denominator is with what was given to me. All right, let's take a look at the next one. So that's just putting the question back for us. Let's look at the exercise number 3. Again, notice what I did here. I put in a plus sign for positive and C for cancer, right? Just to make it easy to write down. What's the probability that I have cancer given that I had a positive result, test result? Well, it's the probability that it's positive given that I have cancer times the probability of having cancer divided by the probability of getting a positive, which will be the total probability of all ways to get positive. Because there are multiple ways to get a positive, right? Getting a positive when you do have cancer, along with getting a positive when you don't have cancer. That's the total probability of getting a positive. So again, the top numbers are easy, right? Probability of getting positive given that I have cancer. Where is that on my screen here? What bullet point is that? 90%, right? That's bullet point number 2. What's the probability of having cancer? 1%. So those are easy to find. What's the probability of having a positive result? Well, again, it's the probability of those who don't have cancer getting a positive plus the probability of those who do have cancer getting a positive. And all the data is there in our bullet points. And by the way, these are real numbers as of a couple years ago for women between the ages of 40 and 50 who for breast cancer statistics. I actually got these numbers from another video about Bayes' theorem, and I just liked the example, so I'm using this. I don't remember the exact video I got it from, but the numbers are correct. Okay, so take a look at our path again. The far left little red dot there is our starting point, and we had two options. One option is you have cancer, one option is you don't. So here we have starting point. This means you had cancer, this means you don't. There's a 1% chance that this will happen and a 99% chance that this will happen. Once we know that you don't have cancer, or that you do have cancer, we know 90% of the time the test results will be positive, and 10% of the time they will not. We also know that once we know you don't have cancer, we know that 10% of the time you will get a false positive, and 90% of the time it will read negative. Now that we have the tree and we know the paths to each of the different ways to get to a positive result on a cancer test, we can see the first path there in green plus the path there in blue. If you add up 0.01 times 0.9 plus 0.99 times 0.1, plug that into the bottom of our formula there, and you will get those numbers right there. Agreed? When all is said and done, you get 9 over 108, which I believe I saw that fraction on the board a couple times, which is a final answer of 8.3%. So I'm going to put the numbers back up on the screen again right here and compare them. The only person who was close, now be honest with me, when you said 3%, were you just being funny or were you genuinely thought it would be that?
I was just being funny.
Okay, so
Thought it
you-
would be a lot higher.
Yeah, so what did you think it probably would have been?
Like, you-
8, yeah, okay, good. That's typical. And you see these other numbers here, 40%, 47, 60, 75, 99. It seems like, and that's just our intuitive brains, well, we say it's intuitive, but it's wrong, right? But myself too, you see that and you're like, oh, 90% of the people who have cancer get a positive hit on a cancer test, and I just got a hit on a positive on a cancer test, I've probably got cancer, right? But it's not even close. There's only an 8% chance that you have cancer if you get positive on a test. It's crazy, the difference, right?
Do they preface that before people take tests, or they just freak out?
I have no idea. Yeah, I don't know. The oncologist probably, says, all right, we need to do another test. That's probably what happens. And so, yeah, I don't know how all that works. I have no idea. But this is a real world case where Bayes' theorem is useful. Because, what if they went from this to, all right, start chemo tomorrow, right? That's nuts, right? Because only an 8% chance you actually have cancer, very slim chance. And I love the fact that you did say 3% because, and I'm putting words into your mouth, but essentially your attitude was like, I'm going to say 3 because that's crazy. There's no way it's going to be 3, right? But then it was closer to 3 than we all thought it might be. But in our minds, it seems so ridiculous that it might be that low, which is why you threw that answer out, I'm assuming. So there we go, 8.3%. So this what happens again, we have more data and it helps us update our belief in how accurate something is or whether or not I actually do have cancer. And so going in, taking the cancer test, the doc says it's positive. My belief is I've got cancer. That's my belief. Once I understand the data and I plug it into the formula, I've updated my belief. Now I see, I probably don't have it, right? That's how that works. Now, using Bayesian thinking in the real world, which we probably won't have time to watch that video, but I will link to it, you don't just sit there and plug in numbers in your head, but you think through things like this. And when you can understand these kind of, what is the probability overall of something happening versus what is the probability of it happening in this little small subset of situations versus this subset of situations, and it can change your perspective on things. The more information you have, right? The more you know, knowing is half the battle, G.I. Joe, all that stuff, right?
We also know what percent of the cancer tests, because not every single person of that 99 would take a cancer test, right?
So the question is, of the people who don't have cancer that take the test, what about all the other people who don't have cancer that didn't take the test? Would knowing that information be useful? But
So you
I'm
just assume that everybody takes the test at the 99.
no, you wouldn't assume that everybody took the test. Let's say right now 1 million people have taken it. If suddenly 10 million people took it, maybe that number would change. The number of false positives might change. So having a bigger sample set is always useful for sure. So that's a good point. That probably would make a difference. Yeah. Yeah, good. But that is, and again, what would we do? We'd update our belief based on the statistics we have. Good questions. But what's the point of all this stuff? Keep an open mind, right? We originally thought, all of us, myself included, thought that the answer to this question was going to be at least 50%. None of us thought it was going to be 100%, but we thought it'd be 50, 60, 70%, but it wasn't. So we need to keep an open mind and realize, well, there's more things affecting things than we realize, and this Bayesian thinking can help us update our beliefs based on more and more information. The more information we have, the more we can update our beliefs. So the answer to the question, what's the probability of having cancer given that the test results were positive, is only 8.3%. It's a nice sigh of relief if you did get positive on the test. Any questions about anything that we've talked about today? So just a brief little kind of snapshot here. We're not going to do any calculations or anything. But this is the kind of thing that and I've mentioned this a few times before, where Bayesian thinking can be applied. And this is applied in our world as IT people. Given that this email, whatever email you're looking at, contains the word money, what's the probability that it is spam? I'm not expecting you to answer the question, but I want to know, what stuff do you think we would need to know to answer it?
Total amount of emails that contain, well, obviously, we're only analyzing emails that contain the word money.
So we need to know what percentage of emails have money in it. What else would we need to know?
How many are scams?
How much spam does exist? And we don't even necessarily know that number, right? Because you might have gotten a spam email and you didn't report it. But based on the data we have, what percentage of all email is spam, right? Just like you were saying a minute ago, not everybody's taking a cancer test. So the more people that take it, the more we can update our data. So I'm going to go back and solidly say, yes, that would make a difference, because I originally said it wouldn't, but yeah, it will. So we need to know total number of spam emails that exist based on the data we have, total number of emails that have the word money in it. Anything else?
What are the odds that a spam email contains the word money and a non-spam contains the word money?
So probability which is total probability, right, of it containing the word money, right? Yeah. Probability of a non-spam and a spam having, yeah. So we want to know non-spam emails, how often do they have the word money, and spam emails, how often do they have the word money? That's the data we would need to know to figure out if this one email, that whatever that email is spam. Now look in the book in chapter 7.3, and it has a whole section on some actual calculations with different keywords, and it has some statistics and some numbers in there. I think Rolex is a popular one. If the word Rolex is in there, it's probably spam, right? But take a look at that in the book and read through that. That's like towards the tail end of the chapter. But here's the kind of stuff that we would need. Probability of spam and all, like as we mentioned, probability of spam emails containing money, probability of emails containing money, which is non-spam and spam, right? Which is exactly everything we all discovered. If we had that information, we could figure out what's the probability that this email is spam. So even though we're not going to plug in any numbers here, what I want to just briefly mention is conceptually, how would this work? If the spam filter software on your server, on an email server, it can read the subject line or it can read the email, right? You can just have a text parser that can look for text. That's pretty easy. You guys have probably all done that in Java at some point. Okay, so you can parse through the email, look at it, and then look for the word money, or maybe you've got a list of keywords you're searching for, and you have data on every one of those. So the word Rolex, we have data, and again, I don't know the numbers, but we have data on the word Rolex, how often it appears in all emails, how often it appears in spam emails. We know the probability of spam total, which is going to be the same for no matter what we're looking at. It's just a total probability of getting spam. So this filter can calculate based on the keywords we're searching for, Rolex or anything about dating sites or sex or this kind of stuff. Those are probably all spam, right? Or medicine or this kind of stuff, or money. All of that stuff is probably spam. But the filter can calculate it. And you can tweak the settings on a spam filter. I don't know if you've ever manipulated a spam filter. If you've ever worked on a server, on an email server, you can tweak it to be super sensitive or less sensitive. And you can just have this filter spit out a number. There's a 10% chance this email spam. Now you, as the administrator of the server, you make a decision. Well, what percentage am I willing to risk? If it's a 50% chance that it's spam, should I let it through? If it's a 60% chance, 70% chance, right? Maybe if it's a 10% or less, I'll let it through. So you tweak the spam filter settings as the email server administrator. You tweak the settings, and that's what gets through. And so the filter will say, all right, anything that's less than 10%, and it runs a Bayesian calculation, and it comes up with that number, and it compares it to what the filter's set at, and it lets that stuff get through. That's how spam filters work. So if you've ever tweaked one or had one set, or you worked with the admin person who sets it at your company, and you're like, why am I getting all this spam? And they went and tweaked the filter for you. That happened all the time where I used to work. So this is a real world application, and you can see how this formula could be helpful. We've seen it in the medical world. You can see it in your daily thinking, which is what you will see if you watch this video that you can click to. I'll put a link to it in the video description below. Any questions about anything we covered today, guys?